This is the
go.
All right. Anybody figure this one out yet?
No. I kind of skipped that anyway, to be honest.
That's on the test. I think most of us will.
Let's go over question 1.
I don't think I need to thank you.
You've seen one kind of like this, right?
Right.
What else have they done this with? Not just boats. What else could they do this with? Planes, like a plane traveling against the wind and with the wind.
Train.
Possibly a train.
Cars.
The key to this is there's 2 things we don't know, and those are the 2 things I asked. The speed of the boat. Now, I just want to make sure we understand the speed of the boat when it's in still water and the speed of the current. Is everybody clear on what's being asked? So the boat is traveling in a river, and when it's going downstream, it's not just it's not just moving because of the motor, it's also moving because of the current, right? So whatever speed the boat is going, it's being assisted by the current, so it's actually traveling faster than the speed of the boat alone. Does that make sense? When it turns and goes upstream, it slows down because it's got the speed of the boat, but then the speed of the current is working against it. So that's why the upstream trip took longer, 5 hours instead of 3. So the typical way to approach these is, since they're asking for 2 different things, the speed of the boat and the speed of the current, is just have 2 variables. So I'm going to first get a pencil, let x be, what are they asking for? Speed of the boat. Now what it means by the speed of the boat in still water, if we were to remove the boat from the river and just put it in like a lake, and then how fast would it be traveling? And I'm going to let y be the speed of the current. Thank you. And then what we're going to use is this equation. Distance, try this again, distance equals rate times time. It's one of our good old-fashioned physics equations. Distance equals rate times time. And we're going to have to use that equation twice, once for the downstream trip and then once for the upstream trip. And the reason we have to do it twice is we have 2 variables, right? We talked about this. 2 variables means we have to have 2 equations. So the 2 equations we're going to create are using this formula, and we're going to create one for the downstream and one for the upstream. So downstream, what was the distance?
8 miles.
They're both 8 miles.
Okay, so the downstream trip distance was 8 miles. The rate, well, this is what we talked about a moment ago. The rate downstream is the speed of the boat, plus it's got the current pushing it faster. So how can we describe that using our 2 variables?
3 times the quantity of x plus y.
X plus y. So if we're just talking about rate of downstream, it's the speed of the boat plus the speed of the current. That's the rate. So right here we've got distance. This is the rate. Now I need to multiply it by time. How long did it take?
3 hours.
3 hours. So 8 equals quantity x plus y times 3. That's the distance equation for downstream. We're going to do the same thing for upstream. If we're going to do distance equals rate times time, it's the same distance, 8 miles, but now the rate, it's a different rate because the boat turned around, and we assume that when it turns around, it doesn't do anything with the motor, it just keeps the motor running at the same speed. So the boat is traveling at the same speed, but the speed of the current is now working against it. So it'd be the speed of the boat minus the speed of the current. And then the time for this trip was 5 hours. So all it's left to do is turn these into a nice system of equations. So 8 equals 3x plus 3y, and then 8 equals 5x minus 5y. And then it turns into a relatively simple system of equations to solve. What's your preference on this one? Substitution?
Oh, I would say
Elimination? Probably, my preference would be elimination.
Yeah, I think elimination would be faster.
So I'm going to multiply this top equation by 5. bottom equation by 3. So we get,
You can multiply it, oh, never mind.
yeah, so since one of them's already negative right there, I'm gonna, is that what you were wondering about?
I'm
Yeah.
asking you to multiply by -5, but there's a positive and, yeah, so, I never, go ahead, sorry.
So I'm gonna eliminate the y. All right, make sure I'm honest on this. 30x equals 64. So then divide by 30. Slightly over 2, it looks like maybe. 2. Somebody who's got their calculator out, help me with that. 2.13? Okay, now since this represents an actual quantity in the real world, what are we talking? What's our units of measure here? Hours and?
Speed of the boat.
So it's hours and miles. So this is a rate. So this is miles per hour. Slow boats. It's a rowboat. Somebody's rowing that fast. It's like a kayak.
Oh, kayaks are a little faster than rowboats.
So if that's the speed of the boat, that's x. So this is 2.13 miles per hour. How do we find the speed of the current? Yeah. So you can choose either one of the equations. I'm going to go to the downstream one, and let's see. We had 8 equals 3, and now we already know that x was 2.13 plus 3y. Okay, and then we solve for y. So what do we need? 3 times 2.13. Let's see. 6.39. Yeah, so 8 equals 6.39 plus 3y. Subtract on both sides. Let's see, I'm getting 1.61
Yeah.
equals 3y, and then divide by 3. 0.54. So the speed of the current is about half a mile an hour. What did we figure out on this one?
Y is negative.
X is -6.
-6 and -8? What,
Wait, how did you guys get -6?
let's go through this one. What would we multiply this one by to get rid of the fractions? 6, okay. And then,
Why is it 6?
Because 6 would make all of them common underneath.
yeah, the common denominator there would be 6.
Oh.
And then on the second equation, the common denominator would be 12. So,
Oh, so it's individual for each one. I thought it was for
Right.
all of them, and I was like,
no.
where are we going?
Just do a common denominator for each equation. Now, what you got to be careful on, like here, this first equation, or this first part of that equation, if you multiply a 6, the 3 goes into 6 twice, so it's really a 2 that multiplies with that x. Am I making sense?
Yeah.
So, let's see, that becomes 2x. And then for that second equation, the 6 and the y, or the 6 cancels out, so we just get minus y. With that one, hello, there we go. 3 goes into 6 twice, so it's really a 2 that would multiply there, and you'd get -4 at the end. And then similar thing there on that bottom equation. Just distribute the 12 into each part of that equation. So the first part, the 12's cancel, and you just get x. 4 goes into 12, though, 3 times, so that would be minus 3y. And then when it multiplies there, 2 goes into 12 6 times, so you got to have that 6 carry over to the 3, or multiply to the 3, making 18. The nice thing is this system of equations is numerically equivalent to the one we started with, just has no fractions. So the solutions to this system of equations are going to be exactly the same as the solutions to that one. Which one would you rather solve, though? The one on the right or the one on the left? I'm thinking the one on the right. No fractions. So from here, again, you got your choice. You can do substitution or elimination. I'm going to go ahead and multiply the bottom equation, though, by 2. And
Negative 2, you mean?
let's do negative 2. Good choice. Let's multiply that by negative 2. So then it becomes negative 2x plus 6y equals negative 36. Now with the elimination, x eliminates. 5y equals negative 40. So y equals negative 8. So we're halfway there. To get x, I'm going to go ahead and use that equation right there. So x minus 3 times negative 8 was 18. So that does equal negative 6, doesn't it?
So, when we are trying to get the two, when we're trying to use elimination, we don't have to add something to both of them. We could just be like so you see the top one, we didn't have to like change it, we had to change the bottom one. We can do that.
We can, as long as when you, so what I was trying to do is get opposite coefficients here.
Yeah.
So as long as you can do it with just one equation, you're fine. Sometimes you do have to multiply both, but that's only if, like this one here that we did in question 1, I had to multiply this one by 5 to get a 15 there, and that one by 3 to get a negative 15 there. So that one I had to multiply both.
All right.
So yeah, both of these.
You want us to not eliminate z first, correct?
It's not that it makes it.
Grading.
Yeah, it's not that you can't do it. It's just if it happens to have infinitely many solutions and you've eliminated z, that's what you're supposed to start with is z equals t. So then you have to go back and backtrack. So I don't eliminate z as a first step.
Okay. Even though that seems like
Like here, yeah, it looks like z, but you could also say that like the 2 y's right here.
Yeah. I see what you're saying.
So that's actually how I'm going to start. I'm going to take equation 1 and 3 and eliminate y. That way I don't have to multiply by anything.
I like that. Because you have to go backwards when you do. If you end up with infinitely many solutions, then you end up having to do the parameters backwards. X, Y, Z in the parentheses. So he's suggesting to not do that.
And we'll do one like that. One of these, I can't remember which one, but one of these is infinitely many solutions. And in that case, you don't want to have already eliminated z. Just makes things a little trickier. So right now I've got y gone.
Everything else is pretty simple.
And I'm left with 4x plus 4z equals 16. Is that enough to solve for either x or z?
Yeah.
Just with that one
Not
equation?
that one equation,
No.
no, you've got to go and use the other, but it's really cool how the other one seems to work rather well to eliminate it.
Right, but when we do it again, we want to eliminate the same variable. That's the key.
That's
Is
all we need to eliminate.
you've got to eliminate the same variable. So I've already used equation 1 and 3, so I'm going to use, we could use 1 and 2. So if I take equation 1 and equation 2 down here, I've got to multiply, because if you look at the coefficients of y, one's a 2 and the other one's a negative 3. So I've got to have those be the same number but opposite. One's positive, one's negative. So I'm going to multiply the top equation by 3. And the middle equation by 2. So that top equation is going to become 9x plus 6y plus 3z equals 12. I'm going to multiply that middle equation by, what did I say, 2? So that's going to be negative 8x minus 6y minus 2z equals negative 30. So now I eliminate y. And I can't stress that enough. It's important that you eliminate the same variable that you did in the step above. All right, help me out here. Negative 18.
Now you compare to, I call it 4 and 5.
Yeah. So you take these two equations here and make a system of equations. So now we have a system of two variables, two equations.
Okay, just a question.
Yeah.
Could you, in theory, like divide the top one by 4?
In a roundabout way, you could multiply it by 1/4.
Okay.
So,
It just seems like it works sometimes.
yeah, technically you're multiplying. If you multiply by 1/4, it's the same as dividing. So, and that's actually not a bad idea. I'm just, for the sake of it, I know most people try to avoid fractions like the plague, so, but if you want to do that, that's fine. So I'm going to go ahead and just stick with whole numbers here, but never understood why people are so afraid of fractions.
They're just more complicated, that's all. It's not so much that, I don't think it's frustrating.
I'm scared.
Terrified.
Do they? Okay, then I guess there are people.
All right, so what's happening here? Wait a minute. What's 4 times 18? 72. So my variables canceled.
Uh-oh, which means that there is no solution.
Wait, that's 88, not 86.
Regardless, it's still.
So this is no solution. 0 equals anything other than 0 is no solution. That was a lot of work for... Boo. No solution. I thought one of these turned out to be infinitely many. Maybe one of them does. This one does?
Yeah.
These are both from section 5.2, and I think the next problem is a story problem from 5.2. That'll be a real treat. We'll get to that one in a second.
So we're doing,
So this should be number 4. It says number 3, but the numbering was off. So again, it's up to you. I'm not going to say you can't do it, but again, in the case that this has infinitely many solutions, if you've already eliminated z in one of the steps, it makes the process a little harder because you're supposed to start this process when it says state the solution in terms of a parameter. You're supposed to start that by saying z equals t. So if you've already eliminated it, it's kind of awkward.
But all of them eliminate z.
Yeah. Which is why this one turns out to have, I think this one turns out to have an infinitely many. But yeah, if we take equations 1 and 3 right off the bat, then x would cancel. So if I wanted to cancel x again, we could take those bottom two equations, 2 and 3, but I'd have to multiply that middle equation by 2, so that middle equation becomes 2x minus 2y plus 2z equals 4. So now I took equation 2 and 3, but I had to multiply that middle equation too by 2. And we'll look at that. All of the variables and the numbers cancel. Now just remember, it doesn't always happen in this step. So just trying to be prepared for every possible scenario. If we had gotten another equation in this step, we'd have to combine that with this equation, right?
Wait, what?
If we had gotten another equation here in this step with y and z, then we would have.
You need to you combine the two of those.
Then
solve
and that's
it.
often where you get the 0 equals 0 is when you combine those two. We just happen to get it right here, regardless of where you get it. If you get a statement of 0 equals 0, that tells you infinitely many solutions. So like I said, when I grade these, I am looking for this statement right here. This is,
What if we abbreviate it to just int?
that's fine. That's fine. But it says in the directions, if there are infinitely many solutions, then state the solutions in terms of parameter. This is where we still have to represent a solution, and it turned out to be something like t and then 2t plus 1. So we have to do something like this and have that as part of our answer. So the way we start, if there's infinitely many, is to let z equal t. And then we got to find y and x. So we go backwards through the process. We eliminated x and got y and z here in this equation. So if we just replace that z with a t, then we could say that y minus 3t equals -1. And if you add the 3t over, you get y equals 3t minus 1. So we've got z, we've got y, just need x. And that could come from any of those originals. Which one are we thinking?
The second one.
Second one? Yeah, there's no coefficient of x. That might make it pretty easy. So if we take the second equation, x minus, instead of subtracting y, you have to make the substitution of what?
Each of those are, right?
Of 3t minus. So we're choosing this middle equation there. So it's x minus y, and then in place of y, I made the substitution 3t minus 1. And then instead of plus z, it's plus t equals 2. And then I'm going to distribute that minus sign there, so x minus 3t plus 1. Excuse me. So what we're trying to figure out is what x equals there. We just got to move some things around. If you add the 3t over, but then subtract this t right here, you're going to get a 2t on the right side. And if you subtract that 1, you're going to get a plus 1. So there's our x, y, and z variables. So the other part of this problem is stating your solution in terms of an ordered pair, x comma y comma z. So our x was 2t plus 1, our y was 3t minus 1, and then our z variable was t.
No, I know what I'm talking about.
Can you show
I'm looking
that
at the
bottom
last
left?
page.
No, I got that
I
wrong.
have no clue what's going on the last.
With the optimization one?
Yeah, I have no clue.
Okay.
It's just one class too. Just one class.
That's right.
You can do this.
Believe in yourself.
All right. Did you sign the roll?
Yeah. I have
Okay.
a class.
Oh!
That's your way to always say I'm just gonna
Did you?
This happens.
literally my life.
Are you recording this?
This one's recording, yeah.
Okay, cool.
This one's recording.
Okay.
This could happen. You might want to think, hey, if I ate only sandwiches for 1 week,
I mean, I do that already.
for lunch and dinner.
So we're not eating breakfast, the most important meal of the day.
Nobody eats
We're
breakfast.
starting off
For lunch, it just says for lunch and dinner.
So I'm going to go ahead and label these as my variables, x, y, and z.
Okay.
Well, actually, I'm doing something I told you guys never to do. We got to be specific.
JK.
Let me say x is the number of Mediterranean chicken sandwiches, y is the number of tuna sandwiches, and z is the number of roast beef sandwiches consumed in a week.
You want this in the test.
I mean, I'm supposed to present it that way. I've got to be precise. So x is the number of Mediterranean sandwiches, y is the number of tuna sandwiches, z is the number of roast beef sandwiches. It says right there at the very beginning, a total of 14 meals. Well, let me actually back up a step. If I've got 3 variables, x, y, and z,
3 equations.
I need 3 equations. And that oftentimes is the tricky part, not deciding what the variables are, it's deciding what your equations are going to be. So
And the numbers of sandwiches have to add to 14.
that's, yeah, so if I've got 3 different types of sandwiches and the total number of sandwiches has to equal 14, there's my first equation.
X plus y plus z.
X plus y plus z equals 14. So there's one of them right off the bat. X plus y plus z equals 14. This is
So
just
that's
describing,
Number of chicken, number of tuna, number of roast beef.
this is the total number of sandwiches for 1 week, because there are 2 meals a day for 7 days, so 14.
Okay, let's do calories.
And then the nice thing about how this chart is laid out is
Yeah.
it essentially gives us the other 2 equations. We could do an equation for calories, and then we could do another equation for fat grams.
Okay. Yeah, and because you're gonna have the number of sandwiches for and that many sandwiches times calories.
Right.
And you're also gonna have that also for the fat. Is that what you're saying?
Exactly. So if I do calories, so this is just number of sandwiches. This one right here is number of sandwiches.
350x.
So the next one is 40 calories.
So this one would be calories. So 350x plus 430y. That surprised me that tuna has more calories than it. Maybe it's because of the mayonnaise or something they put in it.
That many.
And how many?
Gotta go for the light
48,
meal.
It's a fish, it's a healthy fat.
Yeah, it's a healthy fat.
Avocado.
I don't know. You've seen whales floating, and they eat fish all day, and they're not the most slender of creatures. So I don't know.
And they only,
This is calories right here.
so we do 18x plus 5.
And then if we want to do grams of fat, it's going to be 18x plus 19y plus 5z. And this person needs to have a total of 190 grams of fat. So this is the... And honestly, that's the hardest part of these problems, is setting up the equations. Now that it's set up, I doubt many of you would have trouble solving it. It's getting it set up.
I think I would go with A and C first.
So yeah, we're going to definitely use elimination method here. And here's the nice thing. I'm assuming this is not going to be infinitely many solutions. So you can go ahead and eliminate z with this one.
Okay.
So if I multiplied this top equation by -5, for example, then I can combine equations 1 and 3 to get -5x minus 5y minus 5z. Oh boy, -50, -70. Somebody better check me on that one. Sounds about right. And then equation 3, we didn't do anything to.
So you can eliminate two, like one from the other, and then use the next equation. You don't have to get all 3 z's out. You can just get 2 z's out.
Right.
Okay. So that would be the equation.
So 13x
Oh.
plus 14y equals 120. So we narrowed it down a bit. And then the next step is to eliminate z again, but with 2 other equations, not 1 and 3 this time. So we could do 2 and 3.
Wait, so we're eliminating the same variable,
We've
right?
got to eliminate the exact same variable as you did in the step 1. So since we chose to eliminate z as first step, we got to eliminate z again in our second step. So yeah, I'm down for equation 2 and 3.
And why is it that we eliminated z? Why is it that we shouldn't eliminate z?
I'm guessing that this one is not going to have infinitely many solutions. The only reason you wouldn't want to eliminate z is in the case that there's infinitely many, because you let z equal t, but I'm pretty sure this one's going to have one unique solution.
Multiply this by
So.
by negative 50.
Negative 58, is that what it multiplies to 290?
Yeah.
So let's do that. Negative 58.
Right?
Let's see, 290 divided by 5. Yeah, that's 58. So 58 times 18.
1044.
1,044. So negative 1,044x. 58.
19 is 1,102.
And then that's going to be another minus 1,102y.
Oh my gosh.
Minus 290z.
And then 190 times 58
Yeah.
is 11,020.
So that's going to be negative 11,020.
Yeah.
So this equation, these numbers that I just wrote, this is the bottom equation multiplied by negative 58. And we got negative 58 because that's what you multiply 5 by to get 290, because we're trying to eliminate z. We did not multiply equation 2 by anything in this one, so we got 350x plus,
Oh, we're running out of space.
yeah. We eliminate z again.
Could we have used a different variable?
Uh-huh. You can do any one you want. So negative, I'm getting negative 694. And then, yep, negative 672y. And negative 6180.
Oh, so we're basically just breaking it down so that we have 2 equations with 2 variables.
Yes, but it's important that it's the same 2 variables.
Yes.
So now we have an equation over there with x and y. We have one here with x and y. So now we can put those 2 together and do this whole mess again. And we are out of room. So if you ever run out of room on the exam, you can just stop. You don't have to finish the problem. Yeah.
It's really big.
Wouldn't that be nice?
Challenge accepted.
I wrote one big letter and I ran out of room. Where am I going to do this here? Okay.
Continue down to the next.
Just draw an arrow and start out.
I'm sure the testing center wouldn't mind if you leaned over to your neighbor. Hey, can I borrow some paper? What do you
Actually,
think?
you're allowed to bring in 3 pieces of scratch paper,
And they'll give it to you if you don't
or
have
they'll
it.
give you 2 in the testing center.
Okay.
So you're gonna wanna do elimination again, right?
Yeah.
Multiply by 48.
Multiply the bottom equation by 48.
The top one.
The top. You're
Oh,
talking
my bad. I was
bottom.
Oh.
mine's the top. Yeah, sorry.
So yeah, I see what you mean. So you said by 48?
Mhm.
And which one is that going to eliminate?
Y.
That's going to eliminate y? Okay.
Uh, 624x plus 672y is equal to 5,760.
Wait, say that one more time.
624x plus 672y is equal to 5,760.
5,760.
60.
Okay. Thank you.
Oh my goodness. Gives us -7.
I'm still hungry because of all these sandwiches.
This is Alex problem.
Yeah. Now we can eliminate y.
So we have 70x, negative 70x is equal to
That's all right.
It's not that kind of sandwich.
Are you sure about that?
I mean, this is math.
This is Mediterranean chicken.
So the answer is x is equal to 6.
X is 60. No, 6, you're right.
X equals 6. That would make a lot of sense.
So, yep, x.
60 Mediterranean sandwiches.
So 6 Mediterranean chicken sandwiches, and then we can go back. Can we go back to the beginning with just one variable?
No, we have to go back to
You
that
got the
other
second
one.
Oh my gosh.
You gotta backtrack.
See where I told you to stay and watch?
So I'm gonna use this one here.
13.
The 13x plus 14y equals 120. So we already know that x is 6. So 13 times 6 is let's see, 78. So that becomes 78 plus 14y equals 120. So then subtract 78. We get 42. So 14y equals 42. So divided by 14, and it's 3.
And then we've got 9 out of the 14, so we know the other variable is 5.
X plus
Yep.
Y.
So the total had to be 14. We've already got 6 chicken, 3 tuna. That's 9 sandwiches. So 5. So I'm going to put a 6 here for Mediterranean, 3 for tuna,
5.
and 5 for the roast beef.
The steamed roast beef.
Well, that sure was fun.
Aren't you so excited?
All right, question 6. This is from section 5.3. Partial fraction decomposition. There were 2 types of problems that we studied in 5.3. One where the directions are clear that we're just finding the form of the partial fraction, which is what is going on here. First thing to determine is how many factors there are. X squared is x times x, so that counts as 2 factors. And since it's repeated, it needs to be written in this form. And then x squared plus 25 squared is another factor that's repeated. There's 2 of them, so I know there's going to be 2 more factors. And since it's repeated, it needs to be written in this form, x squared plus 25, and then when it repeats, the power increases, so x squared plus 25 squared. Now x squared plus 25 is an irreducible quadratic factor. So those are the type where the form of the partial fraction in the numerator requires a linear expression. So since I've already used a and b, I'm going to use cx plus d, and then ex plus f. And since the directions just say find the form of the partial fractions, that's as far as we go. there's 4 factors. X squared counts as 2 factors, and then x squared plus 25 squared is another 2 factors, so there's 4 partial fractions. And find the form just means leave it in that. You don't solve for the constants a, b, c, d, e, or f. Now the next question, question 7, is where we not just write the form of the partial fractions, but we actually solve for the constants and find the values of a, b, and c, etc. So with this one, there's 2 factors of the denominator, so there's going to be 2 partial fractions, a over x minus 3, and then b over x plus 5. Now the next step is to multiply the whole equation by the lowest common denominator. So this denominator is going to be multiplied to all 3 pieces of that equation. When it multiplies here, it's just going to cancel out with the denominator, so we would be left with 9x minus 11. When it multiplies to the a partial fraction, the x minus 3's would cancel, so then a would multiply with the x plus 5. And then when we multiply the LCD to the b partial fractions, the x plus 5 factors would cancel, so then b would multiply with x minus 3. So now we have an equation without any denominators, no fractions, so a little bit easier to solve. And we have 3 variables. We have a, b, and we have x. Now we're not actually solving for x in this equation, which is good because the method I use is called choosing convenient values. We're solving for a and b. Since we only have one equation, we can't solve for a and b at the same time. So what we need to do is cancel part of the equation, leaving the other part. What I mean is, since we're not solving for x, we can actually assign x a particular value. So if I let x equal -5, for example, and I plug that in there, -5 plus 5, 0. 0 times a is 0. So that part of the equation actually cancels, allowing me to solve for b. So if I plug in a -5 here for x, I'm going to get -45 minus 11. That's -56. And if I plug in a -5 there, I'm going to get -8b. And then divide by -8, and I get b equals 7. And I can do the same thing. I'm going to let x this time equal 3, because if I plug in a 3 right here, then 3 minus 3 is 0, so then b would cancel, allowing me to solve for a. So if I plug in a 3, that's 9 times 3, which is 27. 27 minus 11 is 16. And then if I plug in a 3 here, I get 3 plus 5, which is 8 times a, divide by 8, and I get the a equals 2. So then my partial fractions, since a was the variable I assigned to x minus 3, that means one of the partial fractions is 2 over x minus 3, and then b had a value of 7, so it's 7 over x plus 5. Now question 8 was from section 5.4, solving systems of nonlinear equations. Now, even though it can be done graphically, the preferred method, the more accurate method, is using algebra, either elimination method or substitution method. Substitution method doesn't always work, neither does elimination method. In this case, elimination method wouldn't be a good idea, because if I tried to eliminate a single variable, the x's are not like terms, so those aren't going to cancel out. The y's aren't like terms, so those aren't going to cancel out. So elimination method is not a good choice here. Substitution method may work better. I'm going to take this bottom equation and add the x over. So then I'm going to get y equals x plus 2. So now I can take this expression x plus 2 and substitute it in for that y, and that top equation becomes x squared plus x plus 2 squared equals 8. Now I have an equation with just one variable x. So I can simplify this. X plus 2 squared is x plus 2 times x plus 2. If I multiply that together, I'm going to get x squared plus 4x plus 4. If I continue to simplify, I'm going to get 2x squared plus 4x. And if I subtract the 8, I'm going to get a minus 4 because I want to get one side equal to 0. So now I can factor out a 2. And I can divide by that 2. So now we have a quadratic equation that we need to try to solve. Oftentimes the resulting quadratic equation can be easily solved by factoring. It doesn't look like this one can factor. So we're going to have to use the quadratic formula, unfortunately. So opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. We've got 4 plus 8, so that's 12. And then 12 is 2 times the square root of 3 all over 2. So this is 1 plus or minus the square root of 3. So those are the two values of x. So what we need to do now is find out what y equals. Now we had almost solved for y up here, we just know the x value. And now we have two different x values we can plug in. So we need one for x equals 1 plus the square root of 3, and we need another y value for when x equals, actually that should be a negative right there, -1 plus or minus the square root of 3. I apologize. So this was -1 plus the square root of 3, and this should be -1 minus the square root of 3. So the y value is y equals x plus 2. So in this case, x is -1 plus the square root of 3 plus 2. Combine the -1 and the 2 and you get 1 plus the square root of 3. Now, for this other x value down here, we get y equals x plus 2. So that's -1 minus the square root of 3 plus 2. Combine the -1 and the 2, and we get y equals 1 minus the square root of 3. So we have two solutions here. Here we have an x and a y coordinate pair, and here we have an x and a y coordinate pair. So the two coordinate pairs are -1 plus the square root of 3, comma 1 plus the square root of 3. That's from this coordinate pair. And then the other one from this coordinate pair is -1 minus the square root of 3 and 1 minus the square root of 3.
So it starts at 0, 0.
So yeah, this is, I think we talked about this on Wednesday. If both of them are squared, then it's a circle. So that top inequality is a circle. If
The other one's a problem.
and the other one's a parabola. So this last number here, 9, is the square root of that is your radius. So the radius is 3, and the center of the circle
So the
is,
greater than, whatever the n number is, that's the diameter.
Not necessarily. If the radius is 3, then all the way across the diameter would be 6. The square.
Oh, okay. Gotcha,
Yeah.
okay.
So if the radius is 3, then I'm just going to go 3 out from 0, 0 in each direction. And has anybody drawn their circle yet?
It looks weird.
Did you do a dotted circle?
Oh, I didn't do
Ah.
that. It's done, baby.
It's a dotted circle.
You know what?
It's a dotted circle. Now, I have had students where they accidentally did it as a solid and it was in pen, and they just drew an arrow to it and said, that's supposed to be dotted, that's okay. Just as long as you correct it.
You're like, no redemption.
No redemption. Now, I've forgotten something though. Where's the shading?
The shading is going to be inside,
It does, well, it does turn out to be inside, but how did you guys decide that?
You plug zero into those spots.
If both the x and y are 0, then the statement 0 is less than 9, which is true. So we do end up shading inside, so I'm just going to draw little arrows to help remind me that I'm shading inside that circle. Okay, now this bottom inequality is going to be a little bit easier, I think, for us to conceptualize if we put y all alone. So y is less than negative x squared. All I've done is move the x squared over. We okay so far?
Yeah.
That might help us visualize better what that quadratic is going to look like, the parabola. It's an upside down because it's negative x squared.
And then crosses at positive 2.
And the positive 3, what does that plus 3 do?
The y-intercept, right?
What's the vertex?
Yeah. So it moves the graph up 3 units, and it's facing upside down. So if the graph moves up 3 units and then flips upside down, the vertex is at 3, 0. So the vertex is right there, and it's going to be opening down like this, but we've got to make sure it's a little more accurate than that. So how am I going to get a couple of other points? I know one of them. Let me get a different color here. The vertex is here. Oh, the black is trumping it. It won't show up in red. Here it goes. Yeah, there we go. Okay. And if I plug in a 1 for x, just to get a couple of other points, 1 squared is 1, and then multiply it by negative 1, so you get negative 1. And then negative 1 plus 3 is 2. So 1, 2 is on my graph.
Wait. I'm so, like, you went really fast. You just started plugging in. That's right. Okay, my bad.
And then because of symmetry, negative 1, 2 has to be on the graph.
That's it.
That's all.
That's all you need.
Has anybody drawn their parabola yet?
Oh, no.
Is it a dotted parabola?
I didn't vote for that one.
Is it a dotted parabola?
Underline that it's solid, but if
Yes.
it's not, then
So it's got to be a dotted parabola.
All right. Wait.
Because we already know 0, 0 is true.
Wait, why is it dotted?
Because it's a less than, there's no equal.
It's not less than or equal to, it's just less than.
3, so it is true, it's inside of the
Shading, right?
Inside the parabola, outside the-
So,
Less than or equal to or less
wait, you guys are ahead of me. If I plug in a 0 for x and y, then the statement 0 is less than 3,
So you.
which is true.
Shade
You would shade that.
So we're shading, now we gotta try to visualize this. We're shading inside the circle, but also inside the parabola.
so it's only like the inner, there's no hit,
It's just the parabola inside.
So let me do something incorrect. You tell me what I did wrong. So if I'm circling inside the circle and the parabola, what if I do this?
Do that. No.
Because you've got outside the circle.
I've gone outside the circle, right? I've got to stay inside the circle and inside the parabola, so it's just right here.
So wait.
So there's my solution set.
Okay.
Okay, problem's not done yet though.
Why do you have to label it vertices?
The other part of the problem is, where is it? Label the vertices. So different color, the vertices are where the graphs intersect. We already actually found one of them right here. But we've got to find the location of that point, and we've got to find the location of that point. So this kind of goes back to what you were asking. How do I know which equations or inequalities to find that point?
You
the location of that
You
point?
solve for the system.
Oh yeah, because it'll be a quadratic, so it'll have two solutions.
So this point is the intersection of these two inequalities, but if it's just a point we're trying to find and not a shaded region, if it's just a point, we can do an equation and not inequalities. So it would be x squared plus y squared equals 9, and x squared plus y equals 3. If we solve that system of equations, that's, yeah, eventually we will. That's actually going to tell us both points. So, you guys want to do elimination or substitution? It's split. It's split. So I've got two hands. With one hand I'll do substitution. With the other hand I'll do elimination. We'll do it
you're
at the
not
same time.
ambidextrous in this.
Substitution.
It's substitution.
Elimination.
I would actually say let's do elimination, but only because the x squared and the x squared are like terms.
Right, okay,
the
I
Ys aren't.
see. So you could just add in
Ys
something.
aren't.
But do you even have to like?
That makes it that much
you just
easier.
then you just subtract, right?
So you've got to be careful. If you're going to do elimination,
Oh, but we don't have x squared.
let me show you what I mean.
Y squared. We don't have y squared.
If we are going to do elimination, you'd have to multiply the bottom one by -1. And you've got to be extremely careful at this point. Is it true that the x squareds are going to cancel?
Yeah.
Yes. Are the y's going to cancel?
No.
They're not like terms. So y squared minus y is y squared minus y. You have to write it as y squared minus y. And that equals 6.
And then you would.
I'm videotaping this. I'll post it.
Are you, okay.
Yeah.
Record your voice too.
Uh-huh.
It's gonna be all our lovely conversation.
Where it's getting everything. So y squared minus y. Yeah, I'll do those when I get home. Y squared minus y minus 6 equals 0.
Okay, and then you would add 6 to the other.
You'd
No,
solve
you
the
have to,
y.
you do,
You
you would
find
do
the-
the quadratic, this is a quadratic, just factor it out.
Factor. Now I'm going to hit the pause button here. Well, not on this, but
Time out.
what if, let's talk about a what if, because your problem on the exam might be slightly different than this.
Yeah.
Matter of fact, it is going to be. It's not going to be the same problem. It's going to be different. So answer me this question. Why did elimination method work on this one? Why?
Because the terms will already alike.
Because we had like terms x squared and x squared. What if, here's a hypothetical, what if that bottom equation were linear and it was x plus y equals 3?
You'd have to do substitution.
You'd have to do substitution. Did
Because
everybody hear that?
Otherwise, you're gonna
Is
get.
that foreshadowing that I hear?
I don't know. So the elimination worked well in this one because we had like terms x squared and x squared. If this was x plus y equals 3, then you would have to do substitution. And we did. I think there's a problem like that on the review. This is the practice exam. If you look on the review, there's one that requires substitution. This one we're using elimination. You ought to know both and be prepared for both. Anyway, does this one factor?
Yeah. It's 3 and 2.
Y minus 3,
Plus y plus 2.
y plus 2,
Then y equals 3, y equals -2. You plug it into the
y equals 3, y equals -2.
And then you have to plug it into
Both.
both equations. Yes, that's right. No, because it has to
Is it
work for
really
both.
right?
It has to work for both, which means you can plug it into either one.
Can you plug it in for down?
So I'm gonna do this one, the quadratic and not the circle. Well, that was weird. Here we go. So x squared plus y equals 3. I'm gonna plug in my y values now into this equation. So for y equals 3, I'm gonna get x squared plus 3 equals 3. But for y equals -2, I'm gonna get x squared minus 2 equals 3.
Okay. And then you would solve for x.
And now we're going to solve for x. So bumping back up to here, if I subtract 3,
That's going to give you 0.
I get x squared equals 0, which means,
X equals 0.
and what that tells us is one of the intersection points is the point 0, 3.
Right.
And didn't we already knew that one for here was 0, 3. So that one just told us
Right.
the one we already knew, 0, 3. This other equation here, if I add 2, I'm going to get x squared equals 5.
That does not work.
Well, it doesn't work
I can
nicely,
get that,
but
It doesn't work pretty. It's just
x equals plus or minus.
The square root of 5. Which is an imaginary number.
Only if the negative were inside.
Oh, that's right, sorry.
Remember, though, that these represent points on the plane, so for both of these points, y was negative 2,
Okay.
but for one of them I got positive square root of 5, and the other one I got negative square root of 5.
And that would be.
So those are the locations of these other 2 points. This one is positive square root of 5, comma negative 2, and this one over here is negative square root of 5, comma negative 2. And those,
You had to figure those out.
what's that?
You had to know what
And we had to do the vertices.
Right, those are.
That's the end of it?
Yeah, that's it. No. Show us what needs to be the solution. Does that make sense? Like what the answer
This needs to be shaded in,
Okay.
and then these statements, wherever the vertices are, you have to show their
Label them or
location.
show them?
Well, label means you have their coordinate locations next to them.
Right.
Like that.
What do you want us to just to label them?
Or, I mean, you could call this one point A, point B, and point C, and then over here say point A.
Okay,
You could do it that
okay,
way.
Okay, you can do that too. Okay,
Mhm.
cool.
Yeah.
Yeah. From the back, these numbers are wrong. It's actually 8 and 9.
I was like,
Yeah.
I missed it.
So that last one there,
10 first?
this is from section, what was the last section we did, 5.6?
Yeah.
Linear programming. So, like I said, there's a hard style linear programming where it actually is in word form, like a word problem, and then there's these ones where it's
Where it's already
mostly
laid out for you
set
and
up
you
for
just
you.
have to
So
figure.
this is the one we're going to focus on. It's mostly set up for you. What we need to do is graph this. It's a system of inequalities. We need to graph it to find the solution set. And then once we have the solution set, that's when we use this objective equation right there. So that's we don't use this till the very end. First step is to graph that system of inequalities. Now that first statement, x is greater than 0 and y is greater than 0, that's really not something that you have to graph. That's just telling you, remember we talked about this? Yeah, it tells you that everything is going to be in quadrant 1 right here because x and y are both positive in quadrant 1. So when I graph this, I'm only going to graph quadrant 1 and not all 4 quadrants. X plus 3y is less than or equal to 9. That's a linear inequality, so it's a straight line. And it's in standard form. We talked about this also. When it's in standard form, it really is easiest just to leave it in standard form and find x and y-intercepts. So if I want to find the x-intercept, for example, you let y equal 0. So if y equals 0, the x-intercept is 9. And then to find the y-intercept, you let x equal 0. So if x was 0 right there, you divide both sides by 3. So y would be 3. And this is one of the more common mistakes now. Not finding the x and y-intercepts, but making the wrong kind of line. There's a solid or dotted. You got to decide.
It's solid.
This one's solid because it's a less than or equal to. And again, rather than having the line connect through the points, since we're only graphing in quadrant 1, I'm just going to connect two like that. Well, not quite done with that one. Remember shading also.
Oh, that's right, shooting.
Shading.
So if it,
It would be below.
And we're going to use the test point of 0, 0. If x and y are both 0, then the statement we get is 0 is less than 9. So that's true, so we need to shade towards the test point. Shading towards the test point. What's that? Yeah, we haven't got to that second inequality. So I'm just making little arrows to myself to remind me that I'm shading underneath that line towards the test point. Now the second inequality, 2x plus 3y is less than or equal to 12. We're going to do the same thing. It's a linear inequality. We're going to find the x and y-intercepts, graph it, and shade. So the x-intercept would be 6, and the y-intercept would be 4. Ooh, I totally missed that. The x-intercept is 6. And we got to figure out where the shaded region on that one would be too. So if we let x and y equal 0, because we're going to use the test point of 0, 0 again. If x and y are both 0, then we get the statement 0 is less than 12, which is true, so we're shading below that one as well. So if we shade below both lines, then the area that's double shaded is this region. So when we did section 5.5 last week on Wednesday, we called that the solution set. In section 5.6 with linear programming, they call that the feasible region. It's the same thing, feasible region, solution set. Once we have that, the next step is to identify the vertices. So those are the corners of the feasible region. So let's try a different color here. I've got, oh, where'd it go?
Bottom one was
The top one was just showing how.
and the bottom was
So I got this red looking color here to identify the vertices of my solution set, or the feasible region.
Are we allowed to bring in a colored pen to do so on that thing?
No, I didn't put that as one of the options.
I have a question for them.
You should edit.
I have a feeling one of them just kind of walked in,
Oh,
so they let me use it.
I don't
because-
think it'd be a problem.
Yeah.
So who was here on Thursday? Once we have these vertices, what do we do with them?
You find
Just
What
label
the-
them.
We got to find out their coordinate location. So 0, 0, we know that one's the origin.
There's 0, 3, 6, 0, yeah.
This one's 6, 0, because it's right on the x-axis. We have 0, 3, because that's right on the y-axis. The ones that are on the axes are usually easy to identify. It's the ones that are out on the plane that are a little tricky, like this one here. How the heck are we going to find that one?
You solve the equation, it's like
You put two.
you put it into that,
Yep.
maximize.
Well, once we have this coordinate, then we're going to put them
Do
in.
that, right.
But in order to find this coordinate right here, we have to solve that system of equations.
So when if you multiply it by a negative, you will keep sign right, or is that?
We do, but when we solve for that coordinate, we turn them into equations, so they're no longer inequalities. So we get rid of those inequalities.
And how do we know which one to pick?
It's a good question. This dot is the intersection of that line with that line, and those lines are both created by those two inequalities right there.
So it matters which one.
It does, and that's a good question, because we may have a situation where there's more than two lines, and so you've got to be careful. Her question was, how do we know that this point right here, how do we know we're going to use those two equations? Well, that point is the intersection of those two inequalities, so we have to use those two.
So you find x and y, and that's what that coordinate is.
Exactly. So we could do elimination method here, multiply the top equation by -1. What that will do is eliminate y. And that leaves us with x equals 3.
So then you plug 3 in for one of those equations.
And then you plug 3 in. Yeah, this is just like from section 5.1. So once we know x equals 3, we can use one of these, like this top equation. If x equals 3, then 3 plus 3y equals 9. If you subtract 3, you get 3y equals 6.
Y equals 2.
So y equals 2. So that point is 3, 2.
Then you plug that into.
Now, you're right. We haven't used this objective function yet because we didn't know what x and y were. Now we have several x and y's to choose from, and the one that wins is the point that, what does it mean to maximize, high or low? High. If it said minimize, we'd take the lowest one. Because it could say either. It could say maximize or it could say minimize. So you got to read it carefully. Don't just always go with the biggest. You got to read the word. Maximize means the largest, and we have to plug in each of our vertices.
We skip 0, 0.
And we can skip zeros. Just looking at the equation, if both x and y are 0, then z is going to be 0, and we're probably going to find a higher value for z than 0. So we're good to skip 0, 0. So I'm going to find the value of z for a couple of points here. For 6, 0, the value of z for 3, 2, and the value of z, what was my other point? 0, 3. It could, because oftentimes linear programming is used on a large scale for large productions or things of that sort, so
Because you were dealing with like 300 and 400 graph.
in that case,
Like eight different possible things that you, it was nasty.
oh really? No, it's test questions can be a little bit more like this one.
Have you at least a C?
So what am I doing here? When I say I'm going to find the value of C for 6, or Z for 6 comma 0, how do I do that?
Plug in.
Yeah, plug a 0 in for Y and a 6 in for X. So it's 4 times 6 plus 3 times 0 equals 24. For 3 comma 2, it's 4 times 3 plus 3 times 2. That's 12 plus 6, that's 18. And then for 0, 3, it's 4 comma 0 plus 3 comma 3. So that's 9. So 6 comma 0 is the winner. The winner, the actual solution is the point that maximizes your objective function. So 6 comma 0 was the point that maximized it.
So to get full points on that, you have to graph it and you have to.
There's no other way really besides graphing to know where all your vertices are going to be. I mean, you could find this point here by just solving the system of equations. This point right here, by doing this.
Well, in Alex, those large outrageous points was just craziness, and I thought if I had to graph some of those,
Yeah.
like